Hello, welcome to my channel. In this video we are going to be introducing acid-base equilibrium or ionic equilibrium, and we shall start by looking at acid-base concepts or theories that define acids and bases. Before we can continue, I kindly request you to subscribe to my channel and turn on the notification bell so that next time I upload the next video, you are in position to get the notification and you don't miss out on a single content, as we shall be posting the videos in bits. An acid, according to Arrhenius acid-base concept, is that substance which will release hydrogen ions in aqueous solution. So this will give us examples of hydrochloric acid, perchloric acid, nitric acid, sulfuric acid, among others. But one thing we should note here is that when this acid is in solution, the hydrogen ion that is produced won't be existing freely. In the presence of water, these hydrogen ions are taken up by water molecules so that they exist as the hydronium ions. Now, a base is that substance which will produce hydroxyl ions when in aqueous solution on ionization or dissociations. The examples that we get here will be sodium hydroxide, potassium hydroxide, ammonium hydroxide, rubidium hydroxide, magnesium hydroxide, among others. Now, after looking at these definitions, we can find out where the concept is limited. The first limitation there is that the basic or acidic properties of any substance will be restricted to the presence of water as a solvent. So anything outside water won't be regarded as an acid according to this concept. For instance, we have dry hydrogen chloride gas, and this will not be an acid unless dissolved in water, and if it is in any other solvent, even if it can still give out the proton, it won't be the acid according to this concept. And our second limitation is that it cannot explain the acidic characters of salts like aluminium chloride, boron trifluoride, iron 3 chloride when in aqueous solution. Well, it can also not explain the basic nature of ammonia, some metal oxides, as well as the acidic properties of the non-metal oxide, some of them. For example, it cannot tell us why sulfur dioxide is acidic. And lastly, it does not explain the acidic or basic nature of substances in non-aqueous solvents, because the definition says it must have been dissolved in water. So now we look at our second acid-base concept, that is the Bronsted-Lowry acid-base concept, which is also known as the proton donor acceptor concept. This concept defines an acid as a substance that can donate a proton. Now, a proton is just hydrogen ions, and a base is a substance that can accept a proton from an acid. Now, the advancement here is that the acid or a base can be a molecule or an ion, but the other side, according to Arrhenius, it was only actually a molecule that was ionizing, but here we have an ion or a molecule, so that's quite an advancement. Now, in simple terms, an acid is actually a proton donor, or if you don't say that, it can be a protogenic substance. And then a base is a proton acceptor, and if you don't say that, it would be a protophilic substance. And we have some few equations illustrating some reactions. I want us to use the first two to identify what is acting as an acid and what is acting as a base. I've put the colors to guide, but you can't first forget about the colors. Now, we have HCl and water molecule reacting to form the hydronium ions and chloride ions. Now, since the hydrochloric acid is giving its proton to water molecule, it is acting as an acid, and because water molecule accepts the protons from the HCl, it becomes our base. And on the right hand side of this equation, we are seeing it's forming hydronium ion and chloride ion. I've made them blue not by mistake. I wanted us to identify that after losing its proton, the HCl actually produces another base, and water molecule after gaining a proton also produces another acid. If you look at our definition, an acid can be a molecule or ion, as well the base can be a molecule or an ion. Ammonia and water molecule. Now in this case, you are forming hydroxyl ion, which means it is the water molecule that is giving its proton to ammonia molecule. So the ammonia molecule becomes the base, and water molecule is acting as an acid. The same situation in the third equation. We have acetic acid and water molecule. The acetic acid is giving its proton to water molecule so that it forms acetate ion, which is now the base, and the other side we're forming the hydronium ion, which is the acid. So after seeing these three equations, we can conclude that once an acid has lost a proton, the remaining part, or the anion that remains, is still capable of regaining a proton, which means an acid is going to be producing a base upon losing a proton. So that equation can be summarized as an acid releasing hydrogen ion or a proton and then forming a base. Now refer to this ionization of acetic acid. We have acetic acid forming acetate, and we have seen that this acetate ion is now acting as a base, and because it is acting as a base, we look at its acid, the acetic acid. Now the acetate ion becomes a conjugate base for the acetic acid, and the acetic acid would be the conjugate acid for the acetate ion if the reaction was reversed. So if you have a pair of an acid and a base which differ by only a single proton, we're going to be referring them to as a conjugate acid base pair. So which means in this equation we have acetic acid and acetate ion as the first conjugate acid base pair, and water molecule and the hydronium ion as the second acid base conjugate pair. So if you label acetate ion as base in the case 1, coming from acid 1, which is acetic acid, and the water molecule as base in the case 2, which produces hydronium ion, which is the acid in the case 2. We could summarize our equation as acid for the first case is reacting with the base of the second case, forming acid for the second pair and a base for the first pair. So looking at this summary, we can consider these two reactions and many more in the next slide. Water molecule and ammonia, this is what we have already seen and we have been in position to identify. Now we look at hydrocyanic acid and water molecule. It is forming the cyanide ion, which means the hydrocyanic acid is losing its proton, giving it to water molecule. So the first acid is going to be the hydrocyanic acid, and it produces the first base in the first pair as the cyanide ion. So our first acid base conjugate pair is the hydrocyanic acid and cyanide ion. Then the second pair is water molecule and hydronium ion. Now you can pause the video and you identify the pairs in the following reactions. If you look at ammonia and ammonia, you can see that ammonia is acting as a base and as an acid at the same time. Water molecule is acting as a base as well as an acid, forming hydronium ion and hydroxyl ion, and in the case of ammonia is forming the ammonium ion and the amide ion. Now these two molecules, the ammonia and water, that are behaving as an acid and as a base at the same time, are referred to as the amphiprotic substances or molecules, or amphoteric molecules. The other example that we have not shown here is ethanol, which can also behave in the same way like water and ammonia, that is by losing a proton or even by gaining it. Now we have ammonium ions and water molecule. So the ammonium ion is now the acid in this case. Like we said before, the theory says an acid can be an ion or a molecule. So the ammonium ion is the acid giving its proton to water molecule to form the hydronium ion and ammonia as a base. So you can take time and identify the pairs. Bicarbonate ion is also acting as an acid by donating its proton to water molecule to form the carbonate ion and the hydronium ion. Then the hydrogen sulfide with water forming hydronium ion and the hydrosulfide ion. In summary, we have amphiprotic substances like the water molecules, ammonia, ethanol. They all fall under amphoteric substances, but the reverse may not be true, because amphiprotic substances, we are looking at them in terms of giving protons and accepting protons. But if we classify them in the reverse order, you realize that the amphoteric substances include even oxides of some metals like aluminum oxide, zinc oxide, and lead 2 oxides. Now these oxides are not capable of donating protons. Therefore, when we reverse this statement, we would be wrong. So with that, we have examples of Bronsted-Lowry acids: hydrocyanic acid, hydrochloric acid, nitric acid, sulfuric acid, acetic acid, among others. And the examples of the bases, we have ammonium and the organic derivatives of ammonia, that is the amines. So we lastly look at the limitations of Bronsted-Lowry acid-base concept. The first one is that this concept cannot explain the acidic nature of non-metallic oxides. Of course, even the basic nature of the metal oxides. And lastly, it still can't explain why salts like aluminum chloride, iron 3 chloride, beryllium chloride are acidic in solution. Thank you very much for your time. My name is Opio George. I am a chemistry teacher, and in case you have something to share with me, I'm leaving my contacts on the screen. You can put your concern in the comment section, or you can WhatsApp me on the number you see on the screen, or as well email me. Thank you so much for your time. I remind you again, please subscribe and turn on the notification bell. Thank you so much.